Okay, so for part 2 of the 1-4 nodes, we'll do examples 4 and 5 here. Now hopefully all the examples so far you guys felt pretty comfortable with. They should have all been reviewed. These next two questions, although potentially we could have done them last year, they are a little bit trickier, and we're going to see that similar to what we've seen in the first few sections. They're tricky because you have to set up a system of equations. And you guys are certainly welcome to try these. Maybe try setting up a system and see if you can do it. But obviously, if you feel like you need to check them, I will work them out on here as well, and I'll try to explain everything as I go. So this is a fairly common style of question. They give us one person, so in this case Bryce, who takes a stone and drops it from rest at the top of a building, and then another person who throws the stone upward from the bottom of the building, from the ground. And then they ask us at what height or time or anything like that. So at what height will the two stones be at the same location? Will they basically collide, more or less? And then part B, will it reach that same height on the way up or on the way back down? Okay, so to approach this problem, either part of this problem, again, the key is setting up a system of equations. So I'm going to start by identifying all of the information that I know for each of these two stones that are thrown separately. And one of the biggest keys to this problem is keeping the systems consistent with each other. And so because of that, when I define the delta x, I'm not going to just define delta x, I'm going to define the x sub 0 and the x final. In this case, I'm actually going to define the first stone's initial displacement as positive 82 because it's starting at the top of that 82 meter building. So I'm going to define the initial position not as 0 but as 82. The final position I don't know, but that's what I'm looking for, so I'm going to call that x1 or call it h or whatever you want to call it. But that's going to be the variable that hopefully I have in common between the two. The other key here, the other big part is I know typically last year when we dropped a stone from a building, we worked with it being a positive acceleration. But in order to keep my systems consistent, I'm going to define this as a negative 9.8 meters per second squared. That way when I do the stone that has been thrown upward, I can still work with it being a negative acceleration. So again, this is maybe the trickiest but most important key to these questions. You've got to keep the systems consistent, and so I need to make sure it's negative acceleration over here and over when I do the second one in just a second. So then the initial velocity is 0 because it was dropped, it's not moving, and then the time I don't know, but I'll just call that again t1 or what have you, right? Call it whatever variable you want. But I know that the time that it takes for the stone to fall will be the same as the time that it takes for the stone to be thrown upward. So then I'm doing the same thing for my stone that I'm throwing upward from the ground. Right, so I go through all of my variables. Its initial position is 0. Its final position is whatever I defined this as before. So whether I call that h or x1 or whatever you want to call it. The acceleration is also still negative 9.80 because I'm defining downward as negative, which means my initial velocity is a positive 40 meters per second since I'm throwing the stone upward. And then once again, I don't know the time, but I know that it takes the same time for this to rise as it does for the other stone to fall. So at this point, you've got two unknowns for both sets of information, but they are in fact the exact same two unknowns. So I'm just going to set up my displacement, my function as my displacement as a function of time for each of these. So x final equals x sub 0 plus v0t plus 1/2 at squared. I'm just going to plug in that information for each one of these. So my final position, which is what I'm looking for, my initial position here of 82 plus the 0 obviously would go away, so plus 1/2, again, negative 9.80, times the time, which I don't know, but I'm just calling it t1. Do the same thing for my stone that I've thrown upward, right? So again, using the same equation, because I've got the same variable measurements here. So I just set this up, plug this in. Again, that final position is going to be the same, so x or x1 or whatever you want to call it. The initial position of 0 this time, the initial velocity is not 0 because I'm throwing it upward. And then I've got the exact same acceleration piece, right? So setting this up, if you look at this, this is actually a pretty nice system of equations to solve because they're both solved for the same variable. So really, what I can do here is I can just set these two equations equal to one another, right? I can just substitute the left side equal to the right side. So I end up just getting 82 plus negative 4.90 t1 squared equals, the 0 obviously doesn't matter, so 40 t1 minus 4.90 t1 squared. Now the nice thing about this is, if you notice, I've got the exact same acceleration portion on both sides of the equation. So it's actually a very easy equation to solve. I just end up with 82 equals 40 t1, and then when I solve for t1, I get 2.05 seconds. Now do be careful on this one, right, because you've done the tough part, you've done all the tough work, but we have not actually answered the question yet. The question asked us, at what height would they meet? Well, this does, because it only happens at t equals 2.05 seconds. That does tell us for sure this only happened once. It didn't happen twice. And then the other piece is, obviously, I just take it and plug it in. So if I want to find the actual position for part A here, if I want to find the actual position, plug it into either of these two position functions, and actually, if you want to double check yourself, plug it into both, right, because we should end up getting the exact same answer either way. So I took it and I plugged it into this equation. So I get 82 minus that whole mess, and I find that to be about 61.4 meters. So they're going to meet at a height of 61.4 meters, and keep in mind this is with respect to the ground, right? So this is above the ground, because I defined the ground as 0 and I defined the top of the building as 82. So this is all relative to being above the ground. Okay, so I've got that information. Hopefully that wasn't too bad. Part B is actually even a little bit easier. So I know the time that they reach. So in order to determine if the stone is on the way up or down, I just need to decide how long would it have taken my stone to reach the top of its path. So in this case, I'm just going to focus on specifically just the thrown stone information. So again, going back to all that information, and then I want to find the time that it would take to go all the way up. So supposing that the final velocity it reached was 0 at the top of its path, how long would it have taken if we allowed it to go all the way up? So just kind of resetting here, I've got these three pieces of information that I know. Finding the time is pretty easy. So I'm just going to use VOTAP. Right? I'm just going to use my final velocity here as a function of time. So setting that all up, obviously at this point here, I think most of you guys are probably comfortable seeing that it's going to be more than 4 seconds. So that right there would tell us enough. It is in fact 4.08 seconds if you wanted the exact time. But the significance of that is that tells me then it takes 4.08 seconds to go all the way up, but it only took 2.05 seconds for the stones to reach the same height. So my stone that I threw was still on the way up because it hadn't yet gone all the way up to its path. So we know that it is for sure on the way up. So I've got my information there. Again, I just compared the time that it actually took them to reach to the total time that it would have taken the stone to reach the top of its path. If it had been any more than the 4.08 seconds, obviously that would have told us that it was on the way back down. So probably the most involved example from this first notes here. We do have the next one as well. So this one's also fairly involved here, but hopefully not quite as bad as that last one. And again, if you guys want to try this and then check your answers, you are more than welcome to do so. Man drops a rock into a well. Man hears a sound of the splash 2.40 seconds after he releases the rock from rest. The speed of sound in air is 336 is what they're giving us. How far below the top of the well is the surface of the water. Okay, so we've got our well. We're dropping a rock into the well, and then you've got your water down here. The key is that the time, right? If the guy hears the sound 2.40 seconds after he releases the rock, two things have to happen during that 2.40 seconds. The first is the rock obviously has to fall down. The second, though, and this is also still pretty important, right? The sound from that splash has to bounce its way, has to pull its way back up. And that's why they gave us the speed of sound in air. Right? So just like that last problem, one of the keys for us is going to be setting up a system of equations where we identify all of the information we have for both of those variables. Okay, so for the drop of the rock, right, what information do I have? Well, I'm going to call, and you could call x final and x initial. Again, it doesn't matter a whole lot in this situation. So if you want to do it that way, let's do it that way, just to be consistent. I'm going to call the initial position x because that's how high this is, right? My final position, the surface of the water, I would define maybe as 0. So I'm looking for x, I'm looking for how high the stone is. I'm going to go ahead and define the acceleration once again as negative 9.80, and the reason I'm doing that is because I've defined up here as my initial position x, which I'm going to take to be a positive number. So I'm going to still define my acceleration as negative since I'm falling down, and I've defined up here as positive. And then the time, which I don't know, right, but I know that that time would be 2.40 seconds or less, and in fact it would have to be strictly less than that. So at this point I don't know the final velocity or anything, so let's jump over to the speed for the sound returning, right? Well, the good news about that, the sound as it bounces back isn't impacted by gravity, because sound isn't a particle, so it isn't impacted by the acceleration of gravity. So the significance there is I know it's just a constant velocity. So I know the velocity is 336. The position again would be the same as my position before, right? That's the distance, that's the height that it has to return to. And then the key here is the time. The time is not just t1, right, but it's whatever time remains. So just like we've seen a few times in the past, the key to setting this one up is 2.40 minus t1. So then solving this equation, obviously again it's just the algebra at this point, you're just solving a system of equations. So I'm going to go ahead and multiply both sides here by t1. So I get that, and then I'm going to substitute, I'm going to set up my equation for x over here. So my v0t plus 1/2 at squared. Setting that up and plugging that in. And ultimately, anyway, I get that the, so I've got 4.90 t1 squared equals 806.4 minus 336 t1. So substituting all of that in, at this point it's just a quadratic, right? So I've got to get everything to the same side of the equation and then do the quadratic formula. So 4.90 t1 squared plus 336 t1 minus 806.4 equals 0. I just moved both of those over to the other side. And then when you do the quadratic formula for this, you end up getting 2.32, and you get another possibility of negative 70.9, but obviously the negative 70.89 .9 there doesn't make any sense. So that tells us then that it took 2.32 seconds, and keep in mind that was t1, so that's the time that it takes for the stone to fall down. So it takes 2.32 seconds. From this information, I can then go back to either one of my equations to figure out the height. So I could do either one of those equations if I wanted. I'm actually just going to use the constant velocity equation because that one's a little bit easier. So I'm just going to jump right back to this equation and solve for that. So then going from there, I get my velocity of 336 equals the height of the well, and then it is 2.40 minus the 2.32 that I just found. And that's the biggest step, is we're subtracting those two. So we end up with just 0.8 on the bottom, 0.08, excuse me, on the bottom. And then we find our height of the well. So 26.88 meters is what I find that height to be. Anyway, hopefully you guys had some success with this. Like I said, maybe tried this on your own and were successful. If so, awesome. If not, hopefully it makes a little bit more sense after looking at it. So really nothing new here. We just continue to define the two different equations so that we can set up a system of equations for these last two trickier problems. Okay, so that ends then my fourth section of the notes. We'll have one more before the review and the test.